Alright everyone, welcome to another office hours video. In this video, we're going to do another uniform circular motion and centripetal force problem, this time involving a car driving along a banked road. So this is a pretty classic kind of problem that people like to do, and we're going to do a numerical version just because it turns out the algebra for this problem, if you do it purely symbolically, is kind of messy. So let's hop right into it. So in this problem, the usual setup is that you are driving a car, and let's say our car has some mass, 2,000 kilograms, and we're driving along a banked road with a curve, and the road is banked at an angle of 10 degrees. Let's say the road is also following kind of a quarter circle with a radius of curvature of 50 meters, and the road and tires have a coefficient of static friction of 0.7. Our goal is to find the maximum velocity, Vmax, so that the car doesn't slip and we don't kind of overcome the static friction here, right? So there's a couple notes I want to make right off the bat. First of all, the idea is that the banking of the road means that we can kind of convert some of the normal force, which usually points vertically upwards, into a centripetal force as well. So some component of the normal force is basically helping us steer along this circle, right? The other things I want to say are that, first of all, the actual trajectory of the car in space is a flat horizontal circle, right? Let's assume this car is kind of going right in the middle of the road, and we're not kind of sliding upwards or downwards on the slope. And so because we have a flat horizontal circle, we know that the net force has to be pointed this way in order to make sure our car is steering properly along this trajectory. And the last comment that I'll make right now is just that this little piece of information, to not slip, like these quotes, means something very specific, and it's a good idea to keep track of this when it shows up. Basically, when something is just about to slip, this is a big hint that you need to use the kind of static friction as a constraint force. In this case, about to slip means that the static frictional force is exactly equal to the maximum value that it can attain, which is mu static times the normal force. The idea is we're going so fast so that we're about to overcome friction, but we haven't quite overcome the frictional force. And so we have basically attained the maximum friction without causing the car to slip, okay? And so, like I've said in previous videos, solving UCM problems is the same as really just solving a force problem, but uniform circular motion comes with a special constraint, right? We know something about the net force in the case of objects going in a circle. And so, we are going to start, like any other force problem, with a free body diagram. So I'm going to draw out a couple kind of body parts first of the problem. We have this kind of slope here, and the slope makes an angle of 10 degrees with respect to the ground, or sort of to the flat ground. We know that this car is going to be experiencing a gravitational force, so we have some mg pointed downwards. We also know that the car is going to experience a normal force, right, from the road pushing up on the car to make sure it doesn't kind of fall through the road, and so we know that there's going to be a perpendicular normal force. And when I say perpendicular, I mean perpendicular to the road, right? And we've been told that there is some friction in the system. And so determining the direction of friction can be kind of difficult sometimes. The way you want to think about this is trying to figure out which direction the car would slip if there's no friction, right? So the idea is if we drive too fast along this road, then the car is going to not have enough kind of steering force. We're not going to have enough centripetal force. And if the car were to slip, it slips this way, okay? And so the idea then is that the frictional force must be opposing this car's attempt to slip, and so the frictional force must point kind of down the slope this way. And so that means that we must also have some friction static force pointed kind of down the slope here. Also, this problem is on a ramp. And so you might be tempted to kind of do the normal thing when we solve ramp problems, where you set your coordinate axes to be kind of tilted here. It turns out for this problem, it's actually pretty convenient to leave your coordinate axes kind of in the usual up, down, left, right orientation, just because the constraint that we're working with is about the net force being horizontally this way, right? We know that the net force must point kind of horizontally to the right based on the image we have here in the top left. And so one thing that can be kind of helpful is setting your coordinate axes orientation based on the constraints you're working with. I think this problem you can actually do either way, but for this video, we're going to solve it as if we have our kind of usual coordinate system. Okay, so let me grab a copy of these guys here. And we'll go on to our next usual step, which is writing out the Newton's second law equations associated with this free body diagram. And so remember, when we write the Newton's second law equations, we want to write one for the x direction and one for the y direction. And so let's start with the x direction. And so in this case, right, we can see there's a couple forces that contribute to the x direction. First of all, there's this horizontal component of the normal force. And I'm going to draw my kind of coordinate axes here, because we can take this opportunity to label some angles. So because our ramp is kind of tilted 10 degrees, that means the normal force is going to be deviated by 10 degrees from where it normally is. Similarly, the frictional force is going to be deviated by the same 10 degrees here. And so we can use this angle to kind of help figure out what the components of the normal force and friction force are in the x direction. So starting with the normal force, we can try to compute the x component, which is this green component here. And based on our diagram, we can see that this component of the normal force is the opposite side to our labeled blue angle, right? And so this must be then Fn times sine of theta. I'll write sine of 10 degrees directly. Similarly, if we look at the static frictional force, we can see that the x component is going to be this guy here. And in the case of the friction force, it's going to be the adjacent side to the 10-degree angle. And so the frictional force is going to give us a rightwards FFS times, and then cosine of 10 degrees, since, like we said before, it's the adjacent side that we're looking for in the x direction. Okay, and so because the gravitational force doesn't contribute along this direction, these are the only forces we have in the x direction, and so we can write our max on the right-hand side here. Actually, I'm going to slide these over a little bit because I want to give myself some room. Okay, let's do the same thing for the y direction. So for the y direction, we can see that both of our forces from before, the normal force and the static frictional force, also have components here. And so if I inspect my normal force, which is this component here, that is now the adjacent side to that labeled 10-degree angle, right? And so we can write Fn times cosine of 10 degrees. If I take a look at my frictional force, it's going to be pointing downward, or the component of the frictional force along the up and down direction, right, is going to be negative because it's pointing downwards. And so we can write the frictional force component as minus FFS times sine of 10 degrees, since it's the opposite side to the 10-degree angle. And finally, we see that the gravitational force is fully aligned in the kind of downwards vertical direction, and so we can write minus mg here, and this guy is equal to may, since those are all the contributors to the forces in the y direction. Okay, so we've exhausted all of the vectors that we've drawn on our free body diagram, so this must be a complete set of Newton's second law equations. Now, the next thing we have to do is think about our constraints, right? So when it comes to thinking about constraints, the first one we can apply here is that we know this system is undergoing some uniform circular motion, right? And so because these circles that the car is tracing out are horizontal circles, we know that the net force must be pointed horizontally inwards, which in this case is exactly aligned with this kind of positive x-axis, right? So we know that F net must be mv squared over r in the x direction, or in x hat. We also mentioned earlier that the problem tells us the car is about to slip. And so this gives us a hint about the frictional force, right? We know if the car is about to slip, then the static frictional force must have reached its maximum value, Fs max, which is mu static times Fn. And finally, we know that F net y must be 0, because we know this car is tracing a horizontal circle and therefore is not accelerating in the up or down directions, right? So let's go ahead and make these substitutions into our Newton's second law equation. So our first one, the UCM constraint, tells us that the right-hand side of the x equation should be mv max squared over r. The about to slip condition tells us that the friction force must be mu static times Fn. So we can erase both of these, and these become mu static Fn, mu static Fn. And the last constraint we have here is that there's nothing interesting going on in the vertical direction. So this guy is 0, right? And so these are our kind of full sets of Newton's second law equations. So what I'm going to do here is point out the fact that there's a lot of like trigonometric functions. There's the sine of 10 degrees, cosine of 10 degrees. These are just numbers. And it turns out doing this problem algebraically is kind of a pain. And so what we're going to do at this point is just take a moment to plug in our numerical values, okay? So we know that the mass of the car is 2,000 kilograms. We know that the angle of the banked road is 10 degrees. And so this tells us that sine of theta, or sine of 10 degrees, ought to be 0.17. What I'm going to do, by the way, is I'm going to round everything in like a really disgusting way. So we're going to have a few rounding errors, but bear with me. I just kind of want to show off the physics problem solving here. So forgive me for the rounding here. Then we know cosine of 10 degrees is going to be about 0.98. The other things we know, let me add a little thing here. So if the mass is 2,000 kilograms, we know then the weight of this object is going to be m times g, which turns out to be about 19,600 newtons here. Okay, we also know that the coefficient of static friction is 0.7 from the problem, and we know the radius of curvature is going to be 50 meters. 50 meters. Better. Okay, so let's take these values and kind of plug them in, and then we'll come up with our simplified equations here in the bottom right. So let me grab this guy and move it over to the bottom. I'll buy myself some more room here. So our new set of equations becomes Fn times sine of 10 degrees, which is 0.17, plus the coefficient of static friction, 0.7, times the normal force, times cosine of 10 degrees, which is 0.98, equals 2,000 kilograms times v squared over 50 meters. And our y direction equation becomes Fn times cosine of 10 degrees, so we have 0.98 Fn, minus 0.7 for the coefficient of static friction, times Fn, times sine of 10 degrees, which is 0.17, minus 19,600 equals 0. What is a little cramped, huh? Okay, but the upside of this is that all these kind of numerical values, we don't have to carry around algebraically. We can just carry around the numbers so that when we simplify, this gets a little better. So let's go ahead and see if we can grab this, and let's slap it on the next page. And we can work on the last part of this problem, which is going to be just solving. Okay, so as a reminder, this is our x direction equation. This is our y direction equation. And so what I'm going to notice here is that we eventually, this should be V max, we want to solve for V max eventually, right? So we want V max at the end. And so what that means is we should solve for Fn first, right? We want to eliminate Fn. So we'll solve for Fn in terms of everything else and then plug in Fn to the kind of first equation in order to eventually solve for V max. So eventually, so let's start with the y equation here, which involves no velocity and just the normal forces. So the y equation now reads 0.98 Fn minus, I'm going to rearrange the numerical factors a little bit. And I'm going to add 19,600 to both sides so that I can collect my kind of constants on the right-hand side, or really just this one constant. Okay, then what I can recognize is that I can factor out an Fn from both of these terms here on the left-hand side. And the inside of this square brace becomes 0.98 minus 0.7 times 0.17. And so numerically, this turns out to be Fn times 0.98 minus about 0.12. And so this is approximately Fn times 0.86. And this turns out to be about 0.86. Okay? And the right-hand side of this still remains this 19,600 newtons term, right? So we can solve for Fn by dividing both sides by 0.86. And we recover the result that Fn is equal to 19,000, or is about 22,000. And we recover the result that Fn is approximately 22,790, up to a few rounding errors in newtons. Okay, so we have now found the normal force, and we can plug this in our x equation to solve for Vmax. Okay, so after substituting this in, I'm going to come up with an x equation that looks like 0.17 times 22790 plus, and then if I combine these terms now, okay, let's write it out fully. So 0.7 times 0.98 times 22790 is equal to the right-hand side, 2000 V max squared over 50. Okay, so after fully simplifying out the left-hand side, if you plug these into a calculator, you should get this as about 3874 plus 15,630 equals 2000 V max squared over 50. If we add these two together, we are going to get approximately 19,504 with absolutely no respect for the number of significant figures. And the right-hand side becomes 40 times Vmax squared. Okay, and so I can solve for Vmax squared as 19,504 over 40. And so Vmax becomes 19,504 over 40 with a big ol' square root over the top. It turns out this is numerically about 22.1 meters per second, or if you are so inclined, you can convert this into miles per hour, and we find that this is about 49.4 miles per hour. Okay, so we have done the thing. Now that we have the problem completed, I want to kind of talk about the physics part that we did here, right? So all this is just algebra, but remember, the important part, I think, of most physics problems are dealing with the constraints. And so in this case, we recognize that there were three, right? First of all, this car is tracing horizontal circles, so we can tell that the UCM constraint tells us that the net force must be in the x direction to match the kind of plane of the circle. And so we know F net x is mv squared over r. Okay. The other things that we recognize here are that anytime you see the phrase about to slip, this tells you something about the value of the static friction. Normally, we have to treat static friction just like any other constraint force. We don't have a formula for it. We'd have to solve for it. If you're not sure what I mean by that, go ahead and check out the physics qubits about constraint forces, which I'll link in the description. But in this special case, when we know the car is about to overcome the static friction, we can say that the static friction takes on the maximum value, which is mu static times the normal force, right? And finally, our last constraint was that because this object is going in a horizontal circle, we can make a claim that the net force in the y direction has to be 0, right? The vertical level of this car is not changing, it's just driving in a flat circle, okay? And so I'll leave things on this page, actually, because I think this is a more useful physics reference, but that's really all I have for this video. If you have any thoughts or questions about anything we did here, please feel free to leave those in the comment section down below, and I'll get to them. Please don't forget to like and subscribe for more free physics problem-solving tips and tricks. This has been Physics Tutoring Quantized.